Hi, everyone. Welcome to the 55th session of the MedAI Group Exchange Sessions. Good to see you all after the 2-week break. This week, we have Chima Okechukwu from Georgia Tech here with us to speak about his work on X-ray body part classification. So Chima is a master's student in the College of Computing at the Georgia Institute of Technology, and he's a student under Judy Gichoya in the Healthcare Innovation and Translational Lab at Emory. And he's broadly interested in machine learning and applications to medical imaging as well as disease classifications. So thanks so much, Chima, for joining us today. And before we start, do you have any preferences on how you'd like to take questions? Is it okay for us to interrupt you, or would you like them all at the end?
Yeah, we can feel free to interrupt if you have any questions, so I can interrupt them real time. Yeah.
Awesome. Okay, so let's try to make this session as interactive as possible. And without further ado, let me hand it over to Chima.
Nice. Thank you so much for the introduction. So like they said, I will be talking to you about a Kaggle challenge that I competed in as well. So yeah. Before I start, I wanted to say thank you so much for my amazing mentors, Judy and Emory. I really do appreciate their support and taking their time out to guide me through. Today, I'll be sharing some of the lessons I learned from participating in an ML competition. This is a bit less technical from your series, but it's very useful for anyone who's looking to join a competition or is in an ML competition as well. And so this is an overview of pretty much what we'll talk about today. We'll start by talking over the inspiration behind this presentation. Then I'll discuss more about the competition. Then I'll offer some of my non-technical learnings and also the technical learnings or patterns I noticed. Then I'll outline a problem-solving approach for those interested in any ML competition. And finally, I was going to discover the final standing because the competition is over. So, without further ado, we can start with the inspiration. And so this picture here shows one of my mentors, Dr. Judy Gichoya, who's very passionate about learning. Anytime we're working on a project, she would often ask, what did you learn from this? She's very, very big on this question. And at first I struggled because I didn't really think I was supposed to pick up anything from this, but this question is very key because it helps keeps learning in the focus of the experience, which ultimately helps you grow and develop. And so for anytime you're doing, this is just also a general PSAs, if you're doing anything, I urge you to ask yourself this question or view it as a learning experience and ask, what did you learn from this? Or what do you hope to gain from this? And so now I can start talking a little bit more about the competition. So the premise of the competition was pretty simple. They were asking us to build an algorithm to correctly classify body parts in X-rays. So for instance, the image on the left, which is an image of a chest X-ray, is correctly labeled chest, and the image on the right, which is also a chest X-ray, is incorrectly labeled hand. So this is just sort of like the premise for what we're solving for. And why would we want to do this, you might ask? So the organizers of the competition outlined two main scenarios where this is possible or where this will be helpful. And the first one is with the data organization. So they outlined this scenario, and this was a real life scenario where this patient had done multiple X-rays on different body parts on the same day. So this patient had knees, leg, hip, ankle, tilt, and pelvis X-ray. But if you look at the image count in the snapshot of the scans, you see that all those images, all the scans, all the X-rays are incorrectly placed under the knee category. I don't need to explain too much why this is a problem, but one possible scenario, one possible instance is, say you want to do a knee, you want to curate data set for your knees, and you incorrectly pull, like, let's say, hip, ankle, or pelvis as well, or pelvis specific X-rays as well. That's one scenario where this type of model or classifier will be useful. The second is with model dataset validation. So typically what happens is we know where we get our data sets from. Like you typically assume, like, let's say, hey, I'm looking for a chest x-ray, there's tons of publicly available chest x-ray data sets online. But what if you don't know? Or what if you're getting all your data sets real time? What you can do is you can use this type of classifier to validate the images that are coming in. So what you would first do is run the data set through this classifier that can segment into body parts to verify. Like, let's say I'm building a chest x-ray to classify a chest x-ray, a classifier to detect pneumonia in chest x-rays. This validation model can just scan through and say, hey, are these images that I'm getting, are they chest x-rays or are they not chest x-rays? And you can work with that before you actually start with the model. So now for this competition, we're predicting 22 different body parts. They just pretty much segmented the human body and we're like, classify. And yeah, you don't have to read through everything, but just know like some of them are pretty common. Like we have checks, elbow, feet, finger, like pretty much any body part you can think of. The other note is that some x-rays can have multiple labels. So like, I know chest and shoulders were pretty common pairings, as well as let's say feet and ankle are pretty common pairings as well. Finger, forearm, wrists, elbows, those are also pretty common to be paired together in chest x-rays as well. Another note for the competition is that they use what is called the F1 score metric. I'm pretty sure most people on the call are very familiar with what the F1 score is, but what if you're not, what the F1 score does is it measures accuracy using what we call precision and recall. Now, one thing to note about the F1 metric is that it weighs recall and precision equally, and a good algorithm will maximize both precision and recall simultaneously. So one note that comes with that is that a moderately good performance on both is favored over good performance on either precision or recall or one or the other. And so now the way the competition was set up is that you are giving a set of images to test on, right? You're given a test set, a labeled test set, and you're also given a subset of you're given images to train on, a set of images to train on and a subset of the test. And there's also a leaderboard with this competition that constantly updates with each submission. And initially what you're ranked on, how the rankings for on this leaderboard is using your performance on the publicly available test set. They do have a hidden test set, but that is used for the final pairings or the final rankings. And so hopefully, if there are no confusions about the competition or how it's set up, we can now move on to the first set, which talks about the non-technical learnings.
I actually had a quick question about the setup. So,
sure.
Like you said, like many of the body parts can co-occur. So is it like a multi-label scenario, in which case do you need to think about, are you predicting like 5 different things and you have like a top K accuracy or something like that?
Yes, that is very correct. Yes, this is a multi-label. This was intention to be a multi-label problem. So where you would be classifying multiple. For your case, though, to follow up with the question you said, what we noticed was a lot of the labels there weren't quite often more than 3 labels at a time. So like it was just a bit of a common pairing. So like you'll find like wrist, fingers, and like it'll be like this. So it'll be like wrist, finger, hand, or something like hand, elbow, forearm, and things like that.
I see.
So yeah, so it wasn't like, so you can get something like this, but it would be like hand, elbow, and hand, elbow, forearm, and things like that. So. Yeah.
And so did you need to modify the F1 metric for like what would a true positive be? Like let's say you have a forearm X-ray and you have like both wrist as well as elbow, let's say. And
so We didn't specifically, no, it wasn't weighted as well. There was no
see.
weight, no, it wasn't weighted. It was just good.
Okay.
Nice, thank you. Hopefully that answered your question.
Yeah, sounds good. Thanks.
Nice, thank you. And yeah, if anyone has any other questions, yeah, I'll be more than happy to take them as well. So let's, okay. So we'll start off with the first non-technical learning. And this is generally whenever you're starting something, I'm pretty sure most of us do this, but I would want to stress this again. So start by understanding your data. A great first step to do with anything you're doing, especially any of my application, is with some what we'd like to call exploratory data analysis. Now, in statistics, exploratory data analysis is the approach of analyzing data set to summarize your main characteristics. So you're just trying to understand the data set that you were given. Pandas has a lot of statistical function and also a lot of visualization tools. So it's a very good tool to use here. It's a very good API to use here. In our case, we were looking for two main things. The first one was what the images would look like. So what does like a forearm look like versus a wrist look like? What does a chest versus a shoulder data set look like? And the other thing we picked up was the frequency of each of the targets. And so this is just what like a random subset of the data set would look like. So you can see there's a bit of chest, lower leg, abdomen, lumbar spine, thoracic spine. If you look, the second image kind of shows the multi-label property. I don't know if you guys can see my mouse, but that kind of shows the multi-label property of the data set. Now, the next thing we did was with the frequency count of the label. So we're given a lot of labels, right? So I want to see what's the distribution in the data set. And the finding was very interesting. So there are about, like I said earlier, there's about 1,300 or 700 images in the data set. And more than half of them are for chest x-rays. So this is a very big class imbalance. And this was what directed our next few approaches or next few strategies as well. And so which is why I strongly suggest always start with the exploratory data, try and understand, pick up patterns in your data, because that will direct how you move and how you can do well. And so next one is choosing an approach that addresses these problems. So from the exploratory data analysis phase, we discovered two main things. The first one was, like I said, the huge data imbalance. The second one is the few training examples that we had. So in total, we're given about 1,700 labeled data set, which is not very much if you know about like classification problems. You can't really train a good model typically on this data set size. And so the approach we chose was to use, I think it's called the Mira data set. I think it's also by Stanford as well, was to use the Mira data set. So the first thing we did was we trained a classifier, what I like to call the Mira classifier. And we trained a classifier that can identify body parts in Mira. So but those were typically upper body parts. And then what we did with that first step, with the model from that step, was we sort of used this to build a feature extractor for the next step. So we would run our own images in the data set, run it through that Mira classifier. And then essentially what we've done is we've translated the feature space of these images. So now we have much smaller subset, and then trained as what I call the simpler classifier. So like random forests or SVMs or items like that on those classifiers as well. This is what it looks like pictorially. So you have your data set, and then what we do is we use the Mira classifier to do feature extraction, and then run those extracted features through a much more simpler classifier, and then predict the output. Since this is a multi-label, since at this point we're still treating this as a multi-label problem, and what we do is then we'll train each classifier. So there are multiple classifiers for each of the labels as well. And so the key thing, I remember I felt very, very excited, very, very good when this was done. I was feeling very, very happy when this was done. So I submitted my results, and yeah. So the F1 score I got was about 0.84. At this point, we're also ranked, I think, 34th out of about 100 people in this competition at this point. So not bad, but I felt like the effort, the result did not really justify the efforts that went into it. And yeah, that brings me to my next point. Did you have a question? I think
Yeah, I had a quick question. So did the Mura data set label set also overlap with, like, are they basically 22 classes also in the Mura data set?
No. So the one thing we noticed was for the Mura was typically upper body parts. Oh. So it was just really, the main thing was just we wanted a classifier that was able to pick up signal about the X-ray body part. So we trained on a similar problem, which was to classify, that was a good catch, which was to classify, I think, of course, which was to classify, I think with Mira, it was like chest, hand, shoulder. It was pretty much upper body parts as well, but yeah. And if we had another thing you might be wondering is why not just add the Mira data set to your data set? But if you notice back to this, a lot of the ones we don't have are the lower body parts. So if we had added the Mira data set, that would have actually skewed our data set even more as well. So yeah, like I said, pretty much this was a very somewhat disappointing result, but it was a good first start. And that brings me to my next point, which is keeping a positive attitude and having a growth mindset. So one thing is just to be persistent and consistent and try it. Other thing is I want to take a time to talk about a growth mindset, which means that your abilities aren't stagnant. And that is where you hear this thing called growth versus fixed mindset. A growth mindset is someone who believes that you're pretty much, your abilities aren't set in stone and they can be learned. So you typically hear this learning, which is why I urge you to keep asking yourself that first question of what do you hope to learn? Because that'll help you keep you in a growth mindset as well. Yeah, so the other thing I picked up after that submission was to pretty much have an open mind. So typically, a few of us, typically what will happen, or what I see is sometimes you kind of fix with one style or one approach to solving a problem. So for me, that was meant using Keras and TensorFlow. That was something I was very familiar with, but you have to have or keep an open mind and be able to explore in other, in this case, APIs or other ML applications as well. So for me, that was Fast AI. And yeah, the first thing I did was, so I decided to start again with Fast AI. So I tried a much simpler approach with this one. I just trained, I was just like, didn't have much to lose, just try it. And yeah, I trained, I remember, I think I saw a notebook on the competition with Fast AI, and they used DenseNet, so I chose DenseNet as well, and I tried that as well. And the results, yeah, pretty decent. A bit of a step up, a bit of a nice little cake up as well. Yeah. And so this kind of got me hooked on Fast AI, actually. So I started reading more, trying a lot more. And that brings me to this point, leveraging your resources. So Kaggle is a pretty open source, Kaggle competitions, this competition was in Kaggle, and it's a pretty open source, pretty open, it's a very community-based style of competing where resources can be shared. So you can share notebooks and you can ask questions, you can talk, and actually talk to competitors as well if you like. So since my last exploration helped, because I just looked through and I found one on Fast AI, I decided to try this, and this was where I started reading a lot of the publicly available notebooks, started reading a lot of the discussions. And one thing that I tried to do was I started picking up patterns that they were doing that I wasn't doing, or I wasn't doing and they were doing. And these are some of the three main things that I found out from that. So we all agree, and for this, we all agree, or we're all in agreement that this is a multi-label problem. Unfortunately, the way the data set was curated, the multi-class approach seemed to favor it. And I think that's because what they did was they labeled the images and then split them up instead of splitting them up and then labeling the images. So what happens is that the test and the training with the first approach, they both have the same labels and they both have the same, they'll both have the same distributions as well. Versus the second approach where you can just you split the data set up and then give it to your testers or annotators to say, okay, label it for me. And so that was one thing I found was treating this as a multi-class problem got higher performance than treating it as a multi-label problem. So that's the strategy we switched up. For those who aren't too aware, who feel like the line is too blurry, so with a multi-class problem, you're only predicting one class. So let's say that's like your typical cat, dog, bear, anything. You're typically producing one class. With a multi-label problem, what you're doing is you're saying, hey, there's different labels that can come up in the same image. So like it could be a cat and a dog are in the same image, or a cat and a bear are in the same image, that type of thing. The other thing was I found out from reading a lot of the notebooks that the focal loss was really, really helpful. So that would also address the weight imbalance as well. And one I don't advise people to do it, but another pattern I found with high scoring notebooks was, since there was a very little training set, what a lot of people did was they instead skipped out on the validation set. I strongly do not advise you to do this in any real world. Again, this is typically why we say competition models aren't really real world applicable, because there's no way to validate or check your image. So because of the limited training size, what a lot of people did was they forego the validation set as well. And so with that, I adapted all of this, and let's see where we stand, where we stood up. So, and yeah, so this was a bit bigger. We're now at 0.92. So just to recap, we just came in from 34th out of like 100 teams to about 15th. And that's a huge jump. And that's pretty much relevant to my next point, which is celebrating your small wins. So this applies not just in competition or anything like that, or just projects, but also just personal. I think a lot of times we focus on our failures, what we don't work, or like we only celebrate the big wins, but I think it's very, very important and valuable to do it as well. It also helps keep you going and keeps you motivated if you celebrate and acknowledge your smaller wins as well. And so next point, one big thing I really like about Jeremy in the Fast AI, he's the author of the Fast AI book. Yeah, I read the Fast AI book. He's the author. One thing I really like is this philosophy, which is to just do it and experiment. So a lot of times you hear this thing where it's like, I'm not really sure if this will work. I don't really know if I don't know what to do with this, but he'll just say, just try it. So we had a lot of experimentations going, a lot of ways to try it. And sometimes I think you can make assumptions on this. So I assumed because of my previous work or because of my previous, I understood that typically the features in X-ray images are typically nuanced. So you typically use like in general, some deeper neural networks tend to fare well, or more complicated networks tend to fare well. But this was not the case in this experiment. And a much more simpler approach, a much more simple network would do that. So again, it's just to validate, to just tell you to just try it and yeah, work from there. other thing was pretty much just continue. Like I said, I started reading the Classifier book. I think I've read it I read it a few times during that course of the competition. It's a very easy read, and I highly recommend it to anyone. Even if not just for the framework, has a lot of helpful advice, tips, and resources as well. And so the other thing, I experimented with a few network architectures. I also experimented with one other strategy I learned called test time augmentation, which I picked up from the book. And yeah, I tried that. And so with that one, with everything between the experiment and the new test time augmentation, let's see how we fared. And so this time we came up to 0.93. And yeah, our current rank at this point was around 3rd as well. And so I think the winner at this point was the smaller VGG network. So I had a few, I think VGG, DenseNet, and ResNet, residual network. And this one worked with test time augmentation, and that helped me break into the top 3 as well. So, yeah. And so one other thing I noticed, going back to the understanding or working with your data, was, again, this is not an ad, but I really like that book. But one thing the book really advises you is to load up your training data and to look at the batches. So while I did that, I found out that there was a lot of instances of mislabeled images. And once I simply just corrected those images and retrained my classifier. So by mislabeled images, I meant, like, I don't know about you, but I've never had an X-ray with my chest and my feet. That was a label. Or like you'll get something with your hand and your skull. Like there was a few. There were at least 10 instances of mislabeled images. So we corrected those as well. And doing all that and then we retrained our model on that as well, and rerun the experiments using this corrected images as well. And with all that, we got to this point. And so, yeah, at this point, this is pretty much where we were. Yeah, we finished first. We came around first in this one, and the result was around 0.94. And so, but this, if you go back to the, thank you. If you go back to the very early slide, I mentioned there are 2 data sets, right? The very publicly available data set and the private or hidden data set as well. So I'll present those findings after, but before we go over there, I wanted to talk about the technical learning. So, and this part is going to be very, very relevant for anyone who's trying to get or is in a competition, because there are a few patterns. So I've read a few of the, like, after a competition is done, typically what happens is the winners would announce their approach or their strategy. And I found some very consistent, like pretty consistent methods that were used. So the first one, and the very, very popular one, was called test time augmentation. So if you're not familiar with test time augmentation, so typically what will happen is when we're done training an image and we want to test and we want to get inference or performance on the test data, what we would do is we would say, hey, how is this model, what value is this model predicting for image A? And then we'll store the predictions for that image. Now with test time augmentations, what you do is a bit different. And this is why I really like it, is that you would make multiple versions of that image, is that you would make augmented versions of that image, run those predictions on your test model, and then either do the average or maximum predictions, or like like you can do, like, let's say let's say you're predicting 2 classes. If 2 out of 3 of them predict 1 and the last one is 0, you could take the average of those predictions, or you could just say 1, since that's the value that would predict the most. And this is really cool, and I strongly urge anyone to try to do this regardless, because it helps for a few reasons. It doesn't add any extra training time, but it does increase your inference time, The other thing is it increases the confidence of your predictions, which is very, very useful. And yeah. And so this is by far one of the most consistent one I have seen with almost any competition winner is with test time augmentation. And the value I've seen it also playing around is about 6 to 8 augmentations as well. So they'll typically make around 6 to 8 augmentations as well. Another one is with the progressive resize. So the Fast AI team, what they did, and this is what helped them beat, they competed in their own competition, and I think Germany's competition. This helped him win against, I think, Google as well, Google and Intel, which are very big, although they were using very small computation models. So typically what happens is with neural networks, the size, they pick up the kind of features that we want. The size doesn't really change the accuracy, but typically if you have bigger images, it's more likely to pick up a lot more features than if you had a smaller one. So progressive resizing, but that's with larger images. On the other hand, smaller images train faster. And so with progressive resizing, you're kind of taking advantage of both. And what you do is you start off training small images, and you do that so that the training is quicker, but then you use larger images, so you're picking up more features on the images as well. This one,
I had a quick question here, Chima. So
yeah.
This is super interesting. So when your model, I'm assuming, takes a fixed image input size, right? So so even if you resize, like even if you get a small image, do you resize it to bring it to the dimensions that you're? I see.
Yeah. So you would typically what they did was they would resize the batch. They would resize the incoming batch as it was coming in. This one was a bit more difficult to implement in our much well-known like Keras or PyTorch, but with Fast AI it's pretty easy, and that's another reason why this is not an ad for Fast AI, but it's a very good library. It's a very good library. It has.
Do you have any choices on what kind of interpolation that you use for? Like,
yeah.
I'm assuming
Yeah. Actually, no. There are some defaults, but I didn't touch them when I was trying them. I didn't touch it when I was trying it. I did not touch it when I was trying it. No.
Got it. Okay. Thank you.
Yeah. This one typically doesn't affect performance too much, but I know this one definitely does. This one definitely does. Even beyond the competition, you can definitely just, for anything you're doing, you can try it, and it will definitely help. So one big question that comes up is what type of augmentations do I use? I would recommend using the same augmentation to use for your validation set. Yeah. Now the last one is mix-up. So this is big for me because typically with like with augmentation, you don't know what type. There are some cases where you're not sure what type of augmentation to use. And typically, like, let's say you're doing a one where, like, if you remember that's why it's good to look at the images. In the subset of images, there are about 2 or 3 chest images there. None of them were upside down. So if you do like a rotate, it wouldn't really fare very well, right? Or items like that. So mix-up is pretty helpful to decide to automate the data augmentation. This is also another one I found that was very popular with a lot of the winning approaches as well, was mix-up, almost always mix-up and test time augmentation with, if anything, test time augmentation with very peculiar value of 6 iterations over it, 6 to 8 iterations over the augmentation as well. And so with this is typically what it would look like. Is with mix-up, you would, let's say, this is what Fast AI did for us, was if we wanted to predict, let's say, cat or dog, and then it will sort of merge them and do sort of like a hybrid between the two. So pretty interesting application. But yeah. And so now this is during and after the competition, I started looking up like, okay, what's a good strategy for someone who wants to get involved or who's starting to get involved with ML competitions. And this is what I found almost always consistently was the creators will say, start off with the exploratory data analysis to understand your data. And so if you fly blind, because that is where you would typically find a lot of nuances or strategies that would help with your pattern, is to start with the exploratory data analysis. The other thing is to come up with a quick and simple approach. So you want to start very simple. And after that, then you can iterate on it, and then you can start adding all the other things like mix up, progressive resizing, or even test time augmentation to that as well. You can also play around with it. This is also where a lot of times people play around with different augmentations, play around with different network architectures or things like that. I recommend usually starting with, if you're unsure, just start with 3. I do kind of like a simple neural net, a residual neural net, and then a dense net. The pattern between these 3 is kind of like the skip connections are getting more and more dense, just to see if any signal is being lost between the input and your output as well. And the last one, kind of like our last signings as well. I think competition ended, 2 weeks ago. And so these are kind of our final standings. So there's good news and bad news with that, I'll say. So we finished 5th overall out of the 115 teams on the hidden and the public data set. We also came second on the public data set as well. And last but not least, we came 20th on the small hidden sample size as well. So yeah, and yeah, thank you. Thank you for the time. And yeah, if you have any questions, comments, or concerns, do let me know. Thank you.
Wow, this was awesome. Congratulations on the competition standings. And yeah, I'll leave the floor open for questions as well. So maybe I can actually get started with a question. Oh, I see that Ramon has a question.
Like contrastive learning. Could you elaborate on that one? I haven't heard of that one, Ramon.
Well, it's a model training paradigm that other people have been using, like self-supervised contrastive learning, where for fine-tuning the model, instead of maybe training for the body part classification on Mura, you would just train it on pairs of very similar images and dissimilar pairs. Or if you had like the same image, you do some type of transformation and it looks a little bit different. And usually the idea is that you train them using this training scheme. The features are usually helpful for you to distinguish between categories. Like if they look very different.
I see. No, I didn't try that one. No, I didn't try it. That's another one. I'm also doing a second competition as well, so we can try that there too.
I was curious if they'd ever released the hidden test sets data distributions, or
no, they did. No, they did. No, they didn't. I think that might be also perhaps maybe just I like the patient privacy. Maybe that one wasn't properly annotated, but I don't they did not. But what's interesting is with the overall performance was also done with the corrected images. So the competition organizers actually acknowledged that there was that they were also mislabeled images, and so they reran everyone's, and that's how we came.
Oh. I was curious since you have a huge data imbalance problem, did you also calculate like F1 measures for each class and see which was really well performing versus not that well performing?
No, I didn't. We tried, I think, because they said they would take the knee F1 score. I think we did for chess one was the most obvious one. That was the one that the model was performing, but typically it came off with like the more subtle ones was like the ones behind the especially the lower body. That was where we went. That was where we went on performing as well. No.
I see.
I was gonna ask, did you work with other people, and how was that experience, or did you like to do it by yourself?
No, I did. This is not a solo venture.
Yeah.
Huge shout out to Nethra. She's not here, but if she sees this, huge massive shout out to Nethra. Also worked with Ramon. Thank you for your advice. Iman was also advising us. Judy was also advising us. Lots of help. But yeah.
So how was it like, I guess, organizing or like interacting with other people and like getting deadlines ready?
It was very helpful because especially when I started experimenting with the different, so I had kind of like a table of like so I had a baseline, just no extra stuff. Then I would have something with like test time augmentation. Then I would have something with like mix up. Then I would also have like all the models. So it was very, very helpful in terms of like keeping and then everyone would pick which one they wanted to do. So that was very, very helpful. And we'll just report back our mean F1 score on that. And so pretty much one thing that helped was I put anyone who used it to work. So yeah. It was very interesting because I think one thing that is very crucial with that is since it's an experiment, you want your data sets to be the same. So one thing we did was we kept a subset just to test, and that was what no one changed that. We all used the same. You can change every other thing, but don't change the subset that we keep for that. Yeah.
I'm wondering, during your exploratory data analysis, do you find a lot of like noisy labels or noisy data points, and do you try to remove them or correct them?
So we didn't have, because of the very small data set, we didn't have the option to remove them. So we just corrected them. So our lab also has radiologist, Brandon, and he was helping me relabel some of the images. I mean, some of the mistakes are pretty blatant. Like some had feet that weren't feet, and so there are only about 1,000 images. So I had to go. It was very easy to like go through all of them. So I'll pull up like, let's say all feet. Show me all feet images, and it'll pull it up. And then I'll look through and say, oh, this one doesn't look like feet, and relabel that specific image.
Sounds good.
Thank you.
Thanks.
So did you try k-fold cross-validation also? Because I know that one advice you gave was like actually not use a validation test for.
Yeah, so I remember I tried that with the first approach. With the first approach, that was what I did, was with like, I think it was 5 folds I tried with that, because you have, essentially you're not training this big network, you're training like a bunch of small ones. So you could very easily do that. Yeah, so I also did try, it was with the k-fold validation. Yeah, it was with the k-fold validation. But even the winning competition, if you go back to they said that they didn't have a lot of images in like their validation set. Not very advisable for if you're going to deploy or give this to anyone. It's not a very good model. It can win the competition, but it's not very applicable outside of that space.
Did the winning team like actually talk about what other strategies they use, or is that code publicly available? Did you compare?
The one I saw was with the second place solution, and they did a very, very similar approach. Also with Fast AI as well. They also use Fast AI. I think they used a lot more different augmentations than we did doing training, which was the main difference. So I think, I can't remember what the process is, but it's like contrast imaging was another. We did not use that for this. Yeah, that was also another big one. Because I think it came out 2 days ago, so I read that one as well. Yeah. But they use test time augmentation. It's almost always consistent with text time augmentation.
Awesome. Are there any other questions for Chima? Okay, I guess if not, thank you so much, Chima. I think that was a great talk, and we learned some philosophical life lessons also on the way. So I think that was pretty cool.
Nice.
We'll put up the talk on YouTube later today, and then we'll share the link with folks, and we'll see everyone next week.
Nice.
Have a
Thank
good
you
rest
all.
of the week.
Thank you all, and yes, have a great week
Thank
and
you,
weekend.
Chima. Thank you, everyone.
Bye.